Euclidean quantified geometry. So in other words, I use some material tools to analyze geometric objects. So the geometric object of great interest to me, so we call this object flag variety. So by flag, let me denote it by this. So this will be the set of, say, all the subspaces. So you have this guy. So this will be 0 origin inside of V1, V2, up to Vn. So such that the dimension of Vi equals to that. So this is what we call a flag. So when it's a full flag, because it contains all the dimensions, so you pick a vector space over C. So I look at the flag. The flag has to do with a chain of subspaces. Okay, so you have dimension 1, dimension 2, dimension n. So the dimension n is a V. So such that the dimension of I is I. So we've got this a full flag. So and the set of all that is a set, but it's also a variety. So because when we say variety, not just a variety, it's a projective variety, but it can be embedded inside the product of projective spaces, which I'm going to do now. But before we go into that, so the question is that you can drop some choices in between. Now, I can drop dimension 2, I can drop dimension 4, so I will still have a chain. Okay, but that chain that I have is going to be incomplete chain because it's not the full chain. So in incomplete chain that you have, you can look at the set of all that also. So that would be set of incomplete, called a partial flag variety. So you can have maybe you want to pick so dimension 3, dimension 4, dimension 5, maybe you are doing with dimension n, so you can have that also. Okay, so this is full flag, the full flag variety, partial flag variety, and the special case is that you can decide to say, okay, yeah, no, I'm only interested in one subspace. I look at the set of that, so you can just take dimension 2, and you look at the set of that. So in that case now you have G, R, so K, say K in N. So we are talking about the set of all K subspaces in N space. So this will be the set of V, that is a VK, okay? So where VK is where this guy for the dimension. You have the subspace that you have here. So you have this K. So in this case now, so this is a special case, so we call this one grass linear. Okay, and grass linear is generalizing projective space in the sense that if K is 1, not dimension 1, so we are talking about all the lines. Let's say dimension 2, and talk about all the lines through the origin. So we are talking about a set of lines through the origin, that is the PV, is a projective space. Okay, dimension 1. So now the question now is that, first of all, I said this is a set, but you can endow this with the structure of the variety. Because when we say variety, we are geometry, when we say variety, it's not, it has to do with the zero low-cost of polynomial equations. So we are looking at the set of zero low-cost of polynomial equations. But in this case now, so let's start with this first. Okay, let me start with this. So it's a projective variety because I can embed it. I embed it, K, and I can embed it into the, this is n choose K. Okay, so this is called a Plugger embedding. Okay, Plugger embedding is also it's not difficult to see. So now, for this guy now, how do I, if I pick subspace of dimension K, I can express as a row space. In other words, I can write it as a matrix of say K by n. Is that not? So for example, now if I do this on dimension 4 now, so I say I pick 2 now, so I say like GR24. I can embed it into say P5. So in this case, I can look at 2 by say 2 by 4, A1, A2, A3, A4, B1, B2, B3, B4. So how do I embed it inside this space? So you take this as an element of each one of them. So instead, this one you want to look at W1, that will be determinant of this, because they're linearly independent. Yeah. So if they're linearly independent, I don't know how the minor that runs it. This will not be 0, that will not be 0. Okay? So you can take this first one, so and that will be like I say, A1, B2 minus B1, A2. You have that. So that's the first one, A12, A13. I mean, that's a W14, W23, W24, and W34. So you have that determinant now. So that's one we constitute the ordinate inside this space. So, but the question now is that I want to look at what will be, because this one is a close embedding. I want to know the equation for the equation that you want to have, and you want to know what is the relation among this one. Okay, so if you look at this, will go to the, this will go to the, this will go to the. That's if you look at 1, 2, W24 minus W13, 13 W. This is 1, 2, 3, 4. W13, 1324, and the plus say W14, W23. So if you look at that, this will be 0. And this means that this is an hypersurface because it's defined by only one equation. So it's an hypersurface in V5. Okay, because it's defining the equation. Okay, so if that is the way to talk about it. This is the simplest case that I look at. So, but if you get to this point now, so I will see those as a projected variety. So you are going to look at it that the embedding is that you look at this as the product now. So the product, this will be like I say FP. So you embed it inside the product of say n minus 1, k equals 1 into p into n say n say nk. Okay, so you get to this point. For example, now for P, or if I say my F4CN, that is a 6-dimensional, so this will be embedded inside P3, P5, and the P what? And P3. So that is the embedded. So, but it is given by 10 quadrants, okay, so not an hypersurface. So that is kind of thing that I look at. But I'm interested in the cohomology of flat variety. So by cohomology, so an imaginary and also a multi-equivariant cohomology. And when we talk about the cohomology here, so I'm going to talk about the cohomology in this. So there are two descriptions of cohomology. So one has to do with the Schubert classes. This one is associated with the Schubert variety. So the other one is associated. The other one has to do with the T algebra, the Lie algebra of torus. So that's to do with polynomial equation of modulo ID. So for example now, so if I have my C4 in my F4 now, so you have this F4C now. So this guy, you look at the cohomology here. The cohomology, you take question from there. So this would be Z1 up to Z1, Z2, and Z3 modulo ID. Generated by elementary symmetric functions. So, but for example now, first and foremost, what we are going to get to this one later on because this is actually what I do. So first and foremost is that thank you.
Don't let her on, you should finish.
No, just wait, just wait. So first and foremost that you look at this, as I said, it's a projected variety that is also homogeneous.
Yes.
Homogeneous means that it admits the action. The action that is transitive. Yes. Okay, that's just only one orbit. So in other words, so we want to understand what are the torus space points here. Because when you talk about the action, so you have this. So you have to say this one admit, as you see, I would say it admit the action of the linear group act on this FNC. Okay, so you pick flag like this, so you can allow it. You dot it with G, so this is a left action GP. So that's what still give you. It's going to give you another flag with this. Okay, that ought to by that not that that's only one of it.
Yes.
Okay, so what is the stabilizer of standard flag, that will be the Boresov group. So he's talking about the Hessian balance. So it's actually Boresov group. For this case now, this may not be necessarily the potential by 1. So it's general Boresov group, the proper triangular matrix. So in that way I can identify this guy.
Sure.
It's associated with G mode B. Like the G that I have here is actually GNMC. General. Okay, so now the question now is that we want to look at what are the, because here now B that you have here is inside what? It's inside G. It's a closed group inside that place. And the torus that I talk about the mass spectrum, that the torus I'm talking about, the torus here has to do not topological torus that you have something like this, okay, so what have you. I'm talking about algebraic torus. So we're looking at the set of diagonal matrices. That's what we mean by algebraic torus inside this thing. So in this case now, so you have this guy. This one is inside this. This is inside this. Okay, so that is what I'm saying. So the question now is that if this act on this, so this also act on this. So the question is that what are the T space points? That is very interesting to us. So what are the T space points for the flat variety? It turns out that this space point of flat variety is actually the Y group of G.
Yeah.
So when we say Y group of G, yeah, I'm going to stop. So when we say Y group of G that you have there, because we are dealing with joint linear group, the Y group that you have there is actually the normalizer of T in G, modulo what? Centralizer of T in G, and that is W. So we are looking at the set of matrices such that it has only one non-zero entry in each row and each column, and that is 1. Yeah. So, and for this guy now, so in this case now, so this is nothing but SN, symmetric group, the group of permutation. Okay, because if I'm in S3 now, so what I'm saying that we'll be looking at here now. So when we say permutation, of course we know permutation is what? It's a bijective map on the finite set, self-bijective map. Okay, so you have this guy. So this is finite, this is finite. So if this is a bijection, so this is a permutation. That is what we say. It's a permutation. So the question now is that if in the S3 now, so S3 will just be you have a permutation 1, 2, 3, 1, 3, 2, and you know that the permutation you're just permuting. But if I take 1, 3, 2 as a permutation, I can think about it as a matrix. So in this case now, so this will be 1, 0, 0, this is 0, 0, 1, this is 0, 1, 0, and I can like something like that. So this is what I mean by saying that the Y. Okay, so this is what I mean by that. But the question now is that my interest now is this now. So when we talk about T equivariance now, so we can describe the cohomology in terms of graph. Because we have some, if we are given a space that is that has what? That has a finitely many T points. Like this now, the torus now that I have, I will say that this guy that I have, we say that the torus is W. And we know that the order, and we say this is Sn. We know the order of this is what? It's n factorial, it's finite. Okay, so you have this now. So here now, so if you have a space that has finitely many T space points, finitely many one-dimensional orbits, then you can describe the cohomology in terms of graph, what we call the moment graph. Okay, so for the cohomology in the nutshell, the cohomology that I have for F4, now this is the graph, I'm to heteron. Okay, this is graph that I have now, but the question is that you can look at it as a polytope when you take the converse of everything that you have, but this is just the skeleton. Okay, so this is where we can describe the cohomology of F4 in form of the T equivalent cohomology in terms of this. Okay, and the question now is that because I see the combinatorial work, so recently now I begin to look at when we talk about this embedding, I look at the degree now. We have various ways. When we talk about degree in, if I write S squared plus Y squared, S squared, say that S squared. You write S squared plus 3x plus 2 equal to 0. And I ask you, what is the degree? We say of degree 2. Is that not true? So this is a position of degree 2, but that is algebraic. But geometrically, what do you mean by degree? Geometrically has to do with the intersection of this the number of intersections you have. Okay? So when you take the space, you intersect with the hyperplane. And that's the notion of degree. So the question is, then this embed, how do I describe degree? So for Graspina, people have described degree in various ways. They look at the impact polynomial to describe degree. They use theories to describe degree. But today, I'm telling you that I've been able to describe degree maybe during the, if I'm going to give any talk in quantum now. So I'm going to, that's the degree, I'm going to be able to describe the degree of the Graspinian that I have now, just combinatorially in terms of permutation. in terms of permutation. So we have the degree that we have. So what I'm saying in essence is that you have the degree for this one that I just done. This degree of a G. Let's say for G2 now, G24. We know that that is what we call Schubert calculus. Don't ask me for what is the measure. I will not use measure, so you can understand. So you have this. So K, this will be to 4, and you have the IPA. That is the IPA. So this will be your. Okay, but I've been able to use the three-phase point like permutation to be able to get this too. What you do now, you pick the topmost permutation inside this space. This will be 3, 4, 1, 2. And you look at reduced score. When you look at the reduced score, you take reduced 2. And that is very profound. So maybe I should stop
there. So does your work relate to any form of K theory?
Oh, great. So yes, so in this area, because when we talk about the core model also, it's also talking about the K theory. So exactly, so this is related to K theory because now some people look at the K theory of flat variety, both ordinary and T-equivariant. In that case, now they are not using Schubert variety, but rather they are using the structure sieve of the Godeni ring and Godeni group to understand this one. Okay, so along that line, so it's related to K theory, but the way it is related not from the point of view of algebraic K theory, but from the point of view of topological K theory. Yeah.
Yes. In that general definition, that flat, the first one.
Yes, sir.
Can they all have the same dimension? All those vector spaces?
That is what I'm talking about when you are talking about the special case. So if you take just one day one, because you are looking at a flag, this is just a flag, then you do the same. You are working, you pick a vector space, n-dimensional vector space over C. So you want to know what is a flag inside this space. A flag is that you look at the subspaces that you have, it can have if you take the origin. And you have to zero down because I'm trying to understand. That is exactly what I say. You have the zero here. So that zero that we have, because we are dealing already when we are talking about vector space, so already it's very important. So the origin is actually a subspace of dimension 1. Dimension 1 is inside dimension 2, and you want to build this thing up to the vector space that you have. So because it contains all the dimensions.
So that V0 is like a single point.
No, it's a trivial subspace.
I say this way that you have said V star. That's not still. I have a V star. So 0 like this. So that's a flat. So this is a point. There's an element inside this guy, inside the set of what you have now. So it says this is an element inside. When we say flag, this is how we define a flag, a complete flag. So because if you say that you have an n-dimensional vector, it's not going to have just only one dimension 1 now.
Yeah.
So this is 1. I can have another V star prime. I can have another V star prime. I can control billions and trillions of them. And now look at the set. That set is I denote by this that what I call it. It's a set, but we can endow it with the structure of a variety. We can endow it with the structure of a manifold. We can endow it with the structure of homogeneous space. So it's very rich. And it's not costing anything. So that is
what. Somebody
yes.
Use your microphone. Is it working? Okay.
I'm just wondering about the homogeneous space defined here.
Yes.
And what did I do? Like in the case
this is not homogeneous space. This is, I'm talking about the presentation is all homology.
Okay. Like I expect that there should be classes in this cohomology.
And that's what we are saying now. So the question that if you have idea that I have inside this is these are the elements E1, E2, up to what and up to say E, for this one that we have E3. Okay, so and you know, this one is coming from you take action of Sn on the what's this on the ring of what? Ring of polynomial. So how does it happen? So the question that you pick an F and a polynomial inside this thing, you pick this one inside. So you have you have so this would be F S lambda 1 up to say S lambda n, this would be n that you have. So but you are looking at S surface points inside this space such that you will take this and you have never for all F for all the sigma inside S. So what you have there, you are going to have what is called a symmetric polynomial. So and this one constitutes symmetric. The element of that will constitute the symmetric S invariant ring. Like S, this is S invariant. It's an algebra. Every symmetric function can be expanded uniquely in terms of elementary symmetric function. Okay, and that is what is going on here. So in this case now, what you have here, this is what we call it invariant ring. But what is the co-invariant ring of this one? The co-invariant ring is this right? The co-invariant ring, because when you study invariant theory, let me explain this. So it's very important. So when you look like invariant theory, so we have the three fundamental questions of that. So because I'm using Sn, you can use G, you can use any group.
Yeah.
So provided if it is finite, so it is reductive. Yeah. And then you have reductive, so this ring, the invariant ring, G invariant ring is finitely generated. So one, you want to understand what are the fundamental invariants. Two, you want to understand what are the relations among the invariants. The second one, you want to determine that you want to get the algorithm that write every invariant in terms of the fundamental invariant. So, and that's exactly what is going on. And these are the invariants, because we have this is the co-invariant algebra for this invariant algebra. And I can use the co-homology of that and divide with this. Now, if I have the classes here, I can use the types of polynomial inside this. The what I call the Schubert polynomials. That's what I'm talking about. And this is the BG, this GG. Yes.
So the Schubert polynomials, does it work?
There will be interaction during the break.
Yes.
So we have taken all the questions from him. Next person, please.